You know, I'm going to throw aside all the rude stuff I say about him. This dude is really smart. He's really scary smart. And 1 minute he can talk to you about artificial intelligence, and it's amazing. And then the next minute he makes an app that turns everybody into Nicolas Cage.
It had to be done.
And what's scary is that he will sit there and laugh at it for hours. Oh, stop.
Right.
Don't get me started on Michael Bay. So I want to tell you guys, look, taking everything this dude says, he is so super smart, and he's a great sport about getting brutalized. He's awesome, and he's always got my back. And I will be at his other conference in Portland.
That's
in
right.
Portland
in May.
Make sure you show up for that one, because I think I'll be even more ridiculous then. All right, but for right now, I want y'all to give the massive amount of love, like insane amount of love, for the awesome, the amazing, the incredible Gant Laborde!
Yeah. Thank you so much, everybody. Okay, so this is me being serious. I have to say quite specifically, I love what I get to do. I love the technology I get to talk about. Of course, I'm part of a bunch of wonderful programs, but the important part is that I get to actually share over 20 years of experience with each and every one of you. And you might know me from the book signing the other day. It's important to also know that I am significantly involved in React Native. So if you love JavaScript, or if you find yourself having to use JavaScript, two different things, you might say, hey, I want to make a mobile app. And if you want to make a mobile app, then yes, absolutely. You can go ahead and make a mobile app in JavaScript with React Native. I have plenty of content about that. I can talk your ear off about that. Come talk to me afterward if you're interested in either AI or React Native. And then also, one other thing I want to say is that I really care a lot about my company. We hire the best of the best. We're fantastic. I love talking to them. So I have to say thanks to Infinite for letting me go ahead and come out and talk to everybody. And to make sure that they know that I'm here, if you take pictures of me and you tweet it, and you say, oh, look at this, Gant speaking and all that stuff, and you tag Infinite Red and you tag me, that's great, because I'm going to choose one person afterward to go ahead and receive a fun little package of a cool little book here, the same book, but also some extra stuff that's in there as well. So take pictures, tweet pictures. At the end, we'll be choosing someone, and that person's going to get something really cool. So definitely. Yeah, tag Jamin. just tell him I'm saying everything wrong. That's the best part. So let's go ahead and get into this. So we're talking about complex problems. And that's a really weird aspect, because what happens here is when computers came along, there was a whole different world of problems. So in the 70s, they were like, hey, I need to figure this out, and I need to solve this problem. So you've heard about all the different sorting algorithms and how fast they are and how complex this algorithm is versus that one. And nowadays, you tend to think, well, that doesn't matter nearly as much. But in the 70s, if you wrote an inefficient line of code, your code finished 3 days after the other person's code, right? So it was really important to think about algorithms. And it came up with all these really cool algorithms. And then scholastically, you might think, this is done. None of you have to come up here and write bubble sort for me, right? Nobody has to come up and do that. As a matter of fact, does anybody know what sorting algorithm JavaScript even uses? Exactly. It actually depends. It's an implementation. It depends on the JavaScript engine. So it's just choosing the best one for you. So to a certain degree, yes, I went to a college, and I don't recommend that for anybody in computer science. It's a terrible waste of time. But we're pragmatists. We have something to build. We're told we have a problem, and then we have to solve it. And so you might think, Gant, I don't need those scholastic things. I want to say, hey, look, 4 years, 5 years, because I went slower, 5 years at university, I have a few things to share here and there. And I think that that's the most important part about my talk. So you say, Gant, complexity is subjective. Thanks a lot for the problems, but I have a large list of them as well. Well, how do you? Do you say, oh, this is a complex problem because The senior developer right here can't solve it, and if they can't solve it, they're the best person at the company. That's a complex problem. Or, how many of you have heard of big O notation? Raise your hand. I did a survey. Tons of people have heard of big O notation, and it just sort of ends there. You're just like, oh, that's bad, that's good. Okay, good. And that's totally fair. So if you say, oh, it must be terrible if it's big O notation of n factorial, okay? And how many have heard of NP or exponential space and P space? All right, getting to see some hands. It's good. And these are where the dragons are, all right? Y'all are all in season 1 of Game of Thrones. The dragons are coming, okay? Trust me, they're coming. So, must be complex if no one's ever solved this in polynomial time. So you say, Gant, I'm not going to run into that problem. Okay. This happens more frequently than you expect. How many of you have heard the traveling salesman problem? First thing about the traveling salesman problem is it's a problem. It should be the traveling salesperson. But given a set of cities, this person needs to go to all these different cities and then come back home. They want to do it the most efficient way possible. How hard was that to explain? That's something somebody could drop on your desk and say, hey, implement this feature. We want this traveling salesperson to go to each city in an effective way, and then they want to come back, and we want the most optimized route possible. All right, that's not too complicated. Let me think about it for a second. You live in city A, and then you want to go city B, city C, D, and then come home. All right, I can code this. That's not hard. Oh, well, let's go ahead and say maybe we go to all of them, and we go to the closest city, the next closest city. Okay, we go from A to B, that's the closest. All right, now you've got a little problem here. You're going to go from there to C, and then you're going to D, and now you're stuck doing this and coming home. You can plug in all kinds of numbers into an equation, and this will come out. This is just a little bit more than as if you'd gone to E, B, C, D, A. That's fine all the way until you're looking at the map of the United States. You just cost that person an extra 3 days of driving time, right? And the most optimized route, if you take a look here, this is the most optimized route of 50 cities in 50 states. You can tell the distance is actually not the answer. So what the hell is the answer, right? So you got somebody who figured it all out a few times. You say, I got an idea. Let's go find out some really good ones, and then I'll just base it off the old answers. Right? Let's look over the corner. Let's Stack Overflow this for a second. We'll copy and paste from them. So we've got our cities, and we're adding 1 to it. No problem. I could do that. When you add that, the most optimized route to that becomes this. Yes! It's working. System's working. Ship it on a Friday. I'm good. Okay, we've got this one. Anybody want to take a glance at that? Say, okay. Well, obviously, once you've looked at all these, the most optimized route becomes... Now, hey, wait a second. That doesn't look at all like the original one. This is a problem. All right, let's do it one more time. See what happens. It's get a little complicated. All right, let's add 1 city to that. What do you think this is going to look like? What the hell is that? And that's the new, proven, most optimized route. Okay. All right. So now you've had this on your desk. You're sweating. People have, torn you up in 3 meetings so far. You say, I got this. Not screwing up again. I'm going to calculate all the possible routes each possible time, and then just take the shortest one. I got it. I'm going to brute force this. As soon as somebody says brute force, we know what's going to happen, right? So, okay, we've got 3 options. Now, you might say it's 6, but it's actually only 3 because mirroring it doesn't matter. If I go in reverse, it's actually the same exact route, okay? So let's go ahead and solve that for 31 cities. No problem, we'll just solve them all. So if a computer can do 10 to the 6 calculations in 1 second, and this is a generous computer, then that means it would finish in 30 factorial divided by 2 times 10 to the 6 seconds. Are we right, LaFrance?
Permutation versus combination.
Yes, exactly. And we fixed it. We solved it. We could just do this, and we'll have every possible route. And by those calculations in that time, it'll be 63 trillion years for 31 cities. you'll have the right answer in 63 trillion years. This is an unfair problem to drop on anybody's desk. Maybe you should, maybe it's a good hazing question. That's not a bad idea. So yeah, salespeople really love that. And then you as a developer, you got surprised by this. And so this is the wonderful thing from university, is that they come in with these problems that have been around since the 70s that they thought people would have solved by now. And so in 2004, we figured out how to go ahead and solve for new primes within polynomial time. But there's a lot of problems out over here that they're evil and they're terrible. And so you don't see them because, if you take a look at these graphs, for instance, if you fold a piece of paper, and I know anybody who's tried to do it more than 8 is laughing. But if you fold a piece of paper in half 42 times, it would go from here to the moon. Isn't that crazy? That's sneaky, right? So, Gant, thanks. Thanks for telling us this made-up traveling salesperson problem. Is that a real problem? Is this something that actually exists? This isn't a problem. This is the. What's in the field specifically, if you could solve the traveling salesperson problem, you would be solving a whole bunch of other problems at the same time. This has been tied to what is called an NP-complete problem. You would be able to solve, not only this, you'd be able to solve folding proteins, which you might have heard about protein folding. If you were able to solve just that traveling salesperson problem, you would be solving cancer. It's a crazy, crazy problem. We can't figure it out. So the way this actually ties into is that we have things called NP problem space. That is non-deterministic polynomial time problems, and problems in a certain space are called NP complete, that we've proven if you could solve one of them, you could solve all these other ones. So here's the complex problem pool. So what happens when you run into one of these? Okay? How am I doing time-wise? Because I forgot to set my timer. Should be doing fine. So the answer here is that instead, we have to trade perfection for performance. And this scares developers constantly. We have to trade having the exact answer, binary 1 or 0, for a fuzzy answer. And that's what's happening when you're getting all these routings, when you're packing boxes into FedEx trucks. Nobody's actually solved that. That's what you have to figure out. So this whole section is called constraint programming. Constraint programming helps you with packing, scheduling, and routing. Okay? And the idea here is instead of actually teaching it the answer, it's a little bit like AI. What you're actually doing instead is you're defining the problem, and then you're letting it come up with a system that's sort of like an economic basis. You have a cost-benefit analysis, and you identify the cost-benefit analysis so that at least it's going on a somewhat optimal path rather than the perfect path. And so there's really cool examples of this. If anybody's a chess player, they might have heard this thing called the n-queens problem. How many queens can you put on a chessboard of a certain size before one can attack another? So you just look at this and you say, oh, okay, well, I could put 1, 2, 3 queens on there. And if I put a fourth one, it would kind of mess things up. But there's actually a way for a 4x4 chessboard for you to put 4 queens on there so that they can't attack each other. So I'm not going to give you the answer to that because if you like chess, that's a fun thing to go ahead and try to figure out. And the answer's all over the internet. But how do we figure that out? We figure it out with constraint programming. So what I'll say here is let's go ahead and let's code real quick. Let's do a little experiment of constraint programming because I said let's solve a complex problem in JavaScript. And we're going to do a scheduling problem. And we're going to use an economic model for a barista system. And the way it's going to work is we're going to assign cost to each particular potential moment. And then we're going to take the cheapest cost item, and that's the one that's going to get that spot. Okay? So what I like to do with this normally, I like to live code it, but we could do it just to have it all in slides. So we have 7 days a week. We've got 5 baristas, and we've got morning, noon, and night shifts, 3 shifts, okay? So we're going to go ahead and code this. And then the baristas gave us their preferences. If they put a 1, that means that they want to go ahead and they want to work that shift on that particular day. And if they so they're telling me which shifts they would like to work. You might be thinking to yourself, oh man, now I have not only to solve this problem that you told me how complex it is, but you also want to factor in that they have feedback on how it is? Yeah, because it's a cost-benefit analysis now. That's the way of thinking about it, and throwing in one other cost-benefit is easy. So let's solve it real quick. Here are our baristas, and there's the requests for their days. So I want you to help me out, because we're going to just live code with question and answer. And if I start going over time or something, tell me now. OK, so here's a little website. And you first put it in there, everybody's got the same exact costs. It's all straight zeros. So everybody is working every single shift, which makes no sense. So you've got right here, if you take a look, number of shifts, you've got everybody here. And then what happens is 21 people are working each shift every time. So that is not correct. So the first thing I want to do is I want to actually, and they're working it in order. It's just basically getting my list back. First thing I'm going to do is I'm going to code randomness. You see right here, first thing I've got is just go ahead and I'm going to give everybody a small randomness inside their cost just to go ahead and break the system up. And then that causes, ta-da, they're all still working, but the list is now going to be randomized. I like that. That works out quite well. So now it's your turn. We're overbooked. So there's this concept of setting a cost to infinity or making something unpickable or causing it too high. So what I can do now is as I'm assessing the different spots, what's the code going to do when it's filled up a particular time slot on the schedule? It's going to take the other people for that schedule and set them as a potential for that spot to infinity. Exactly. And so what we do is we just say it unpickable. So we count how many people have been assessed for that particular assignment. And then once you have anybody over one, because you can't have two people work at the same time, then ta-da, there we go. We're getting there. It's building a schedule for us. So we have this set up. Looks good. What's the problem that we have now? Well, take a look at Sunday. We just have Mark's getting all the work, OK? So we got to fix this. So we were going to get rid of what happens when a person has been working already that day. So do we want them to be able to work that day again? Let's go with no. OK? So then we do this again. We just do what we just did a minute ago. What happens to all shifts for that day for Mark after that? Infinity. We just shoot it up in total cost. So when we go through, if he's already worked that day, and we count the number of times, if it's anything over one, boop, we make it unpickable. We shoot them up to infinity, or we make it some other cost. And when you're using infinity, these are requirements. Because it can't, we've not even entered an economic model at all. We're just making it absolutely unreachable. OK? So, great. So, I found this on the web. Thank you. What's our, so let's see what happens now. Ta-da! We've got that fixed. OK. All right, my next problem I'm going to go ahead and point out here is that I'm going to say specifically that, look, somebody got 7 shifts and somebody got 2 shifts. That's going to be a little dangerous. You know, how come you always giving Becky shifts? All right, so we're going to move that on. So we need to fix that. We've got to get those greedy shifters out of there. So what we're going to do is the more that a person works a shift, I should have made y'all tell me what the code was. OK, so what we're going to do, this is OK, I'll do this one. We're going to figure out what the number of fair shifts is. If it was shifted out, everybody got the fair number of shifts, what would be the maximum of that? And then what happens is we go ahead and we say, OK, once somebody's hit the maximum of fair shifts, they're unpickable. We shoot them up to infinity. You can't have more shifts than like the maximum. And I think that's something like 5, something like that. So when you do that, there you go. You can see we're maxed out at 5. So you're pretty set here with everybody getting a maximum. Oh, no, wrong button. There we go. So you're set here with everybody getting a maximum of 5 shifts. Do you feel what we're kind of doing here? We're just thinking of the problem and we're constraining it, right? You're writing code, constrain the problem. You're not actually thinking of this any other way. And this is the essence of constrained programming. So I'm going to make you answer the next one. So next up, ready? You little shifters. OK, so here's what happens. Oh, did I go too far? OK, it did. So for little shifters, we've got somebody who's got 3 shifts right here. And that's unfair to them because now shouldn't somebody have like 4 and somebody is having 4, like 5, 4, 4, 4, 4, and like have it be fair that way. So the way we can settle this is we can go into the cost model. So what I want to do for the cost model now is when a person gets more and more shifts, they become more and more expensive to assign again. So what would the code like that sort of sound like, just in pseudocode? Well, yeah, the shifts that you have work against you in some way, any way at all. Perfect. So that's exactly correct. So that's what we're going to do. We're actually just, I'm just going to go ahead and add them, but the multiplying would have worked just as fine. So, well, maybe it would have brought some people a 0 shift. So I'm going to do plussing. So we are making them more expensive, and when we do that, look at this. It evens out. So we have 4, 4, 4, 4, 4, 4, 5, 5. So I think this is really good. We've done a great job. We've got an open schedule. Everything's set. Last problem. It's just using our economic model, and it's super easy because it's not hard at all. One person got their request out of 20 requests. Yee. Well, nobody, it's basically we threw that away. So how do we bring that in there? We just bring it into the economic model. That's it. So you asked for it. Here's the code. Sorry, I'm just clicking through. So what we're doing here is that when you are going for a shift that you want, you get a little discount, right? So all I'm doing is I'm dividing by the discount, making it more attractive for the system to select you for the shift that you wanted. Now, if I have a discount and you have a discount and you've worked more days than me and I haven't worked as many days, who gets it? I get it. It'll balance itself out. I've coded in soft and hard requirements to create. There we go. We just coded it together with the screen and all of us, but you understood all the steps. And all I did was here, we have our entire week schedule. The shifts are even out. We have 13 out of 20 requirements seen, and this was done in 0.005 seconds in JavaScript. Woo! Take that, salesman problem. Yes.
So is the assumption that there's no duplication and like no more than one person pick the same day and the same shift?
They can pick the same exact shift with their picks. That's why only 13 out of 20 will go ahead. Well, yeah. So yeah, if 2 people, and then when you take a look at the data, some people do pick the same day. So it will randomize. But the perfection of it is actually, here's the fuzziness of it. There's lots of right answers. It's the most optimal solution is what happens here. And to be honest, I would refresh this page and get like 5 different schedules and be like, you know what this doesn't have a factor in? Mark is terrible at closing on Thursdays. Refresh, oh, a brand new schedule, perfectly optimized. So what's great about that?
Manager bias.
Manager bias. It's absolutely something that can be factored in, or it could be coded in. This is all part of the system there. And what's great about that is, you're right, there is going to be constraints. So when it first came out, everybody got every single shift. We got 20 out of 20 who wanted them got them. And now we got 13. The question is 13 good? Cover that in a second. So we did it. We solved this problem. We were able to just do an economic system for what was an NP problem. So now we learned about words like hard constraints, requirements, infinity. Also, there's minus infinity. And so what happens is when you hear about hard constraints, so we coded this by, but you can get all those ideas up front and then go code it and then come back with the answer. That's another way. You could just get all it. And you need to know what soft constraints are. And here's the funny part. When you get to soft constraints, which aren't requirements, soft constraints can sometimes be, this one's way more of a soft constraint than this. Like, I really, I want them to get the shifts they want, but I don't want Mark to ever close. Okay, well, which one of these is more important than the other? And so you can code that in soft constraints. You just change the weights that you're applying to that. And there are problems where this is the best way to handle this. And there's entire frameworks built around it. So what about bigger problems? I can tell you this. UPS hasn't contacted me for my scheduling program yet, even though we all just saw it solve it in 0.05 seconds. apparently Google's already got something better, so we'll just go with theirs. But there's two fantastic solutions that I really recommend if you want to bring this to your organization, if you want to bring this concept to where you're going. And these two concepts that I really like, one of them is called OptiPlanner. OptiPlanner is mostly led by a Java community, but it has Kotlin, Scala, Python, and it's really, really readable in the way that they do it. It's super cool in that sense. And then, of course, Google had to have a little bit of everything. So Google OR Tools is going with the C++, Python, Java, and C# community. So that's why I didn't write this code in either of these platforms. I would have loved to have, but neither of them right now are supporting JavaScript. And the Google one, I'll be honest with you, it's probably more maintained by Google. They're like doing the work for you in a sense, so it's less community, more likely to work. It's a lot harder to read. It's a lot harder to write and read. The OptiPlanner is a lot nicer to read and write, but you can get your hands on the Google stuff so easy, and it just kind of works, and they'll make 50,000 tutorials for you. So these are two fantastic tools, and the idea here is that I did plug it in, and 13 is the best number you can possibly get. Yeah! So we did, with our little 0.005 second JavaScript answer, I did go into the OR tools for Google, code it up in Python, and it said, this is the best number that's possible. And that's what these tools kind of do. You can actually say things like, hey, only run and give me a solution after 5 minutes. Hey, go ahead and tell me, is this the best it could possibly be? Things like that. So it is cool. These things have bells and whistles that make it reasonable for going ahead and using those systems, but we can code it in JavaScript just as easy for a lot of solutions as well. So I just want you to know, those are where the dragons live. It's unfair to ask people to go into crazy problems, and it gets a lot crazier. There's a whole section of problems. Dude, it's crazy. The people at universities don't have anything better to do. BQP is the set of problems that would suddenly work if quantum computers were a thing. So it would just be like all these would be solved and stuff like that. There's all kinds of different ways that people break apart problems. You could take a whole dive for probably a week, maybe 2 or 3 days, and learn about problem space. And I think that you should, because when you come across one of these, you got to be careful not to let it get you. But at the same time, what do we do when we have a problem? We turn it into a feature, right? Plug your ears, and whenever we screw up, we say that's what we meant to do, right? So what happens is the hard problems are why certain things work. It's why, remember how I said if you could solve NP-complete tomorrow, you would have cured cancer? You'd also make secure socket layer completely useless, and you would destroy the entire economic market. So be careful who you tell, because solving those problems will destroy all website security. So it is important, but we take our problems and we turn them into something that's really cool as well. So I just want you to take away from this, if you're a programmer and you need to have like, oh, true, false, this, that. I don't think that's how it's going to work anymore. I don't want any of you thinking that way anymore. For instance, if you were to do this, you're like, oh, cool, neato, AI drew that. That was good job, AI. I went in there, I typed something like the immortal software developer. And yeah, okay, cool, this is neat. But if you're really good at generating stuff and you put in all of this, then it made this art piece right here that I'm sure I could print out and hang up on the wall somewhere, or people would buy it, or I could put it on tarot cards and sell it, I could do all kinds of stuff. You might have heard recently somebody from Midjourney won an art competition based off of this. And because it's a matter of you being able to tell the AI and you be able to tell computers declaratively what to create, and they are creating things now. And this is how we're going to break into those problems that we aren't getting every single day. These are the new problems. These are the X space problems. So what's interesting is that we need to go ahead and figure that out. And this just blew my mind. Just recently, DALL-E 2 did outpainting. So the woman with the pearl necklace, which is beautiful, They just added a bunch of stuff that wasn't in the original painting and expanded it out and asked the AI to do it. And you could actually see them selecting, choose this frame, don't choose that. Choose this frame, don't choose that. We're directing AI what to do, and they wound up making this. It looks like it's the real whole thing. That's the future of what you're doing. You're thinking. You're a director, you're an artist, you are a creative. If you're in a place that lets you be a creative, you're in the right place. If you're in a place that's not letting you be creative, you're in the wrong place. So the future is coming. I bet that looks ominous, actually. Ah! The future is coming. Think declarative and constrained. So I have to say thank you so much to Infinite Red for letting me come around and talk to people about super cool stuff. They're a fantastic company. If you ever need anything done in React Native, mobile, we're your people. We only hire creative, intelligent people who want to be creative and intelligent all day, and that's what we look for, and that's what we kind of keep. And then also, I will need to say thank you to Brian Stearns. He's one of our employees, and he helped me go ahead and create the JavaScript model for setting this up. It was really awesome. And then also, I think it's time to go ahead and give away the copy of the book plus some fun stuff. So, anybody who's been tweeting out photos and everything like that, so let me go ahead and ask. There was a guy in the back of the room the other day who said, I've never won anything in my life. Is that guy still here? That's you. Do you tweet out any photos? I'd never win the lottery. Yeah, you bought 0 tickets, man. All right. Okay. So, someone who's been tweeting out photos, raise your hand up. Yeah. This is natural. Good direction. All right. So you have the hands raised up. Okay, if you already have a copy of my book, hand down. Okay, we got a clear winner. Okay, here you go. Absolutely. There you go. Absolutely. Excellent. Okay, and then I just want to say this is my second time speaking in person at MagnoliaJS. I have a special place in my heart. Thank you so much for having me here. I hope that we all talk about cool stuff. You want to talk about AI, you want to talk about React Native, you want to talk about the future of computers and our wonderful new overlords. I'm here. So just thank you very much.